All right, welcome to The Explainer. Today, we are diving deep into the one thing that powers every single thought you have, every memory you make, and every move you, make. We're talking about the action potential. So, have you ever stopped to wonder about that? How does a simple thought, like, I should pick up that cup, travel from your brain to your hand? We're talking about signals moving at speeds that can break 200 miles per hour. I mean, how on earth is that even possible inside our own bodies?
Well, the secret is something called an action potential. And you can just think of it as your body's own private, high-speed instant messaging service. It's this tiny, tiny electrical blip that is quite literally the foundation for everything your nervous system does.
So, how does it get that incredible speed? It pulls off a really cool and kind of rare biological trick. It uses a positive feedback loop. Basically, a tiny little nudge gets the ball rolling, and that initial push just amplifies itself over and over again, exploding into a massive, undeniable signal. It's like a whisper that turns into a shout almost instantly. Okay, but before any message can get sent, the messenger itself, the neuron, has to be perfectly primed and ready to go. It can't just fire off signals whenever. It has to be in what's called its resting state. So, when it's just hanging out, not firing, a neuron is busy maintaining what we call the resting membrane potential. All this really means is that it keeps the inside of the cell electrically negative compared to the outside. It does this mostly by letting positively charged potassium ions leak out. You should really think of it like a tiny, fully charged battery just waiting for a reason to discharge.
And that charge is super specific. We're talking about negative 70 millivolts. Now that is not a random number. It is the absolute critical baseline. It's the starting line for every single nerve impulse you will ever have.
Okay, so if the neuron is just sitting there at a cool negative 70, what does it actually take to make it, go? Well, it all comes down to crossing a very specific line in the sand, a point of no return.
See, not just any little poke or prod will do. A tiny, weak stimulus won't be enough to send the message. The stimulation has to be strong enough to push that internal voltage up to a critical tipping point. And that tipping point has a name, the threshold potential.
For most neurons, that magic number is right around negative 55 millivolts. The second, the very instant that the inside of the cell hits that number, it's game on. An action potential is absolutely guaranteed to fire. There's no stopping it.
And this brings us to what is maybe the most important rule in this whole game. It is an all or none phenomenon. The neuron either fires at 100% full blast maximum strength, or it doesn't fire at all. There is no kind of firing. It's like tipping over the first domino in a long line. Once it starts, it's going all the way to the end.
Right. So what is actually happening during that all or none blast? What does that signal look like? Let's break down the incredibly fast, step-by-step electrical wave that zips down the neuron.
The whole event happens in just a couple of milliseconds, and it unfolds in three main acts. First, you get a super fast spike in voltage called depolarization, then an equally fast drop called repolarization, and finally, it briefly overshoots the landing, dipping even lower than its resting state in a phase called after hyperpolarization.
This whole drama is basically a dance between two characters, sodium and potassium ions. To kick things off, that big spike, a bunch of channels fly open and positive sodium ions rush into the cell. Then, to reset everything, those sodium channels slam shut and a different set of channels open, letting positive potassium ions rush out of the cell, which brings that voltage crashing back down.
A really great way to picture this is to think of these ion channels as having different personalities. The sodium channels, they are the sprinters. They open and close in a flash to get the whole thing started. But the potassium channels, they're more like marathon runners. They open and close much more slowly, and their job is to get everything back to the starting line, ready for the next race. So, we've gone through all the microscopic details of how this one little signal works, but so what? Why does this matter? Let's zoom back out for a second and look at the massive, sometimes even life or death importance of this tiny electrical event. Honestly, one of the clearest ways to see just how crucial the action potential is to see what happens when you block it. And some of the most potent examples of this come from nature, in the form of toxins that go right after those ion channels we've been talking about. I mean, just look at this. This is how fragile the whole system is. You've got famous toxins like tetrodotoxin from pufferfish or dendrotoxin from the venom of a mamba snake. What do? They physically plug up those sodium or potassium channels. They completely sever the communication lines of your nervous system, which is what leads to paralysis. It's serious stuff.
And all of this leaves us with a really fascinating final question. If every single action potential is an identical all-or-none spike, how does our brain tell the difference between a gentle touch and a painful poke? How can the exact same signal mean such different things? Well, the secret isn't in the size of the signal, it's in the frequency. It's a puzzle of timing and rhythm, and that's a story for another day.